Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director for Education at IBM Quantum. This is the 12th lesson in the series, and it's the last lesson in the third unit, which is on the general formulation of quantum information. This lesson is centered around a fundamental notion in quantum information, which is that of a purification of a quantum state. A purification of a quantum state, represented by some density matrix, is a pure state of a larger compound system that leaves us with the original state when the rest of the compound system is discarded or traced out. Every density matrix has a purification, and we can learn a lot about quantum states and about quantum information in general by studying purifications. At an intuitive level, quantum state vectors, which represent pure states, are simpler mathematical objects than density matrices. And by thinking about purifications of states, we're able to view arbitrary quantum states of systems as being just parts of something larger but simpler. We'll also talk about the fidelity between two quantum states, which is a value that quantifies their similarity or overlap, and it's often used as a way of measuring how good a particular state is as compared with some ideal state. In particular, we'll discuss the definition of fidelity along with some of its basic properties, and we'll see how fidelity connects with purifications. Here's an overview of the lesson. We'll start with purifications, including the definition and a simple proof of their existence, which tells us how to find one if we need one. Then we'll discuss something known as the Schmidt decomposition of a quantum state vector of two systems, and we'll see how Schmidt decompositions relate to purifications. Then we'll discuss a critically important relationship between any two purifications of the same state, which is known as the unitary equivalence of purifications. And finally, we'll go through a few examples. We then turn to fidelity, including its definition and some of its basic properties. We'll talk about the gentle measurement lemma, which is a very handy fact that ties fidelity back to measurements. And finally, to conclude the lesson, we'll turn to Uhlmann's theorem, which establishes a fundamental connection between fidelity and purifications. Let's start with the definition of a purification. A purification of a state, which we assume is represented by a density matrix, is a pure state of a larger compound system that leaves the original state that we started with when the rest of the compound system is traced out. We can express this more precisely in mathematical terms as follows. If we have a system X that's in some state ρ, meaning that ρ is a density matrix representing a state of X, and psi is a quantum state vector of a pair of systems X, Y, such that tracing out Y from the pure state ket psi bra psi leaves us with ρ, then we say that psi is a purification of ρ. Naturally, the names don't matter. We can name our systems and our states whatever we want, and the ordering of the systems also doesn't matter. For example, if the system Y was on the left rather than on the right, but everything else was the same, we'd still refer to psi as being a purification of ρ, but we'll mainly stick to this setup for the remainder of the lesson, just for the sake of simplicity. And the first thing to say about this definition is that purifications always exist for every density matrix ρ. And to be more precise, every density matrix ρ has a purification like the definition describes, provided that the system Y is at least as large as X, which is to say that Y has at least as many classical states as X. The notion of a purification and the fact that purifications always exist turns out to be critically important, and it's also part of what makes quantum information beautiful. And hopefully I'll be able to convince you of that fact by the end of the lesson. Now let's prove that every density matrix has a purification. And in the process, we'll see how we can get our hands on a purification when we need one. Just like we had in the definition of a purification, let's suppose that X is a system and ρ is a density matrix that represents a state of X. Now consider any expression of ρ as a convex combination of pure states, as we have written on the screen. In words, for some choice of a positive integer n, we have a probability vector p0 through pn-1, as well as quantum state vectors phi0 through phi-n-1, and by averaging the corresponding pure states weighted by the probabilities, we obtain ρ. For instance, we could use the spectral theorem to obtain an expression of ρ like this, and if we did that, we could take n to be the number of classical states of X. In fact, we could take n to be the rank of rho, which is equal to the number of non-zero eigenvalues of rho, counting each one a number of times equal to its multiplicity, and that's never larger than the number of classical states of x, but it could be smaller. On the other hand, this doesn't have to be a spectral decomposition of rho, and we don't need these quantum state vectors to be orthogonal, for instance. Any expression of rho like this is fine. And here's a purification of rho. The sum ranges over the same values as in our expression of rho, and inside of the sum we take the square roots of the probabilities multiplied to phi a tensored with ket a. Here, by the way, we're assuming that 0 through n-1 are classical states of the second system y, so it makes sense that psi is a quantum state vector of the pair xy, like in the definition. It's not actually important here that we use standard basis states of y in this expression. You could substitute any orthonormal collection of states in place of ket 0 through ket n-1 if you wanted to. And now we can check that this is indeed a purification by computing the partial trace over y. Here's an expression of the state that we get by performing the partial trace. The trace of ket a bra b is either 1 or 0, depending upon whether or not a is equal to b, and so the expression simplifies to our original expression of rho. And it's as simple as that. So it's very easy to get our hands on a purification as long as we have enough classical states of y, or alternatively, a large enough orthonormal set to use in place of the standard basis states ket 0 through ket n-1. And by the way, if the number of classical states of y is smaller than the rank of rho, then there won't be a purification, and I'll leave that for you to ponder if you choose to do that. Here's an example. Let's consider the density matrix that we saw several times in the lesson on density matrices. Here we have an expression of this density matrix as a convex combination of pure states. It's not a spectral decomposition, but we don't care. And with almost no effort at all, we can write down a purification of this state by following the recipe. That's not the only purification of this density matrix. Purifications aren't unique, but that's okay. The definition doesn't say anything about uniqueness. And in fact, there's a very interesting relationship among different purifications of the same state, but we'll discuss that a little bit later in the lesson. Next, we'll consider Schmidt decompositions, which are expressions of bipartite quantum state vectors in a certain form that I'll describe momentarily. They're named after Erhard Schmidt, the same Schmidt known for the Gram-Schmidt orthogonalization procedure, but in the case of Schmidt decompositions, they probably shouldn't be named after Schmidt. It's actually mathematically equivalent to something called the singular value decomposition for matrices, which is something that was actually rediscovered multiple times, but that does happen sometimes. But anyway, here's what we mean when we refer to a Schmidt decomposition. For an arbitrary choice of a quantum state vector psi for a pair of systems x, y, it's always possible to write psi in a special form. That form is as we have here on the screen, where r is some positive integer, p0 through pr-1 are positive real numbers that together form a probability vector, x0 through xr-1 are unit vectors corresponding to the system x, and y0 through yr-1 are unit vectors corresponding to the system y. Now, that might not look particularly special until I tell you that both of the sets x0 through xr-1 and y0 through yr-1 must be orthonormal. So why is that special? Well, if we were to pick any basis for one of the two spaces, let's say the x vectors, which correspond to the system x, then we could always express psi in this form, and that would force us to select the y vectors in a particular way. In fact, we do this pretty routinely, like we do with the standard basis when we're setting ourselves up to analyze a standard basis measurement. But in general, even if we choose an orthonormal basis for the x vectors, the y vectors we get aren't necessarily going to be orthonormal. Similarly, if you picked an orthonormal basis for the y vectors and you tried to express psi in this form, again you could, but again, the x vectors wouldn't necessarily be orthonormal. And finally, if you did pick orthonormal vectors for both systems and you tried to express psi in a form like this, it wouldn't necessarily work because you might find yourself in need of some cross terms, but there's only one index in this sum, which is a. So the form is special. But it is always possible to write a given unit vector psi like this, and here's how you can do it. First, compute a spectral decomposition for the reduced state of either of the two systems, it doesn't matter which, but for the sake of describing how this is done, let's look at the reduced state of x. So we're tracing out y. So that means that p0 through pr-1 are eigenvalues of this reduced state rho, and x0 through xr-1 are unit eigenvectors corresponding to these eigenvalues. And by the way, the understanding here is that we're ignoring the terms for which the eigenvalues are 0, because those terms don't contribute anything to the sum. And that is to say that p0 through pr-1 are all positive real numbers. And r is the number of non-zero eigenvalues, counting multiplicities, which is equal to the rank of rho. So that gives us p0 through pr-1, as well as x0 through xr-1, and all that's left is to find the vectors y0 through yr-1. There's only one choice that can possibly work. Those vectors are uniquely determined at this point, and they can easily be found using the simple formula that's shown on the screen. And what's amazing here is that if we define these vectors in this way, then they are guaranteed to be orthonormal, and that gives us a Schmidt decomposition. I won't argue that in this video, but it isn't too difficult, and you can consult the written material for the lesson in case you're interested. Check the video description for a link as usual. As an example, let's consider this quantum state vector, which we obtained as a purification of the density matrix example that we keep coming back to. It isn't a Schmidt decomposition because the 0 and the plus states aren't orthonormal, but we can find one using the procedure that I just described. The first step is to compute a spectral decomposition for the reduced state of x, which is that same example of a density matrix. And here's a spectral decomposition of it, which we saw back in lesson 9. So we choose p0, p1, x0, and x1 as is shown on the screen. p0 and p1 are the eigenvalues of rho, and x0 and x1 are corresponding unit eigenvectors. And so it remains to compute y0 and y1. And if we do this, we get ket plus for y0 and -1 times ket minus for y1. That's not immediate. You have to actually do the calculation to see it, but that is what we get. And as expected, those two vectors are orthonormal, as they will always be if you've done the calculations correctly. And that gives us a Schmidt decomposition. Schmidt decompositions are very handy in many situations, and shortly we'll see what they tell us about purifications. Purifications aren't unique. A given quantum state, represented by a density matrix, will in fact have infinitely many purifications. There is, however, a close relationship that always holds between any two purifications of the same state, and it's sometimes called the unitary equivalence of purifications. Here's how it works. Let rho be a density matrix representing a quantum state of a system X, and suppose that we have any two purifications of that state that are pure states of the same compound system. So, for the sake of concreteness, let's suppose that psi and phi are quantum state vectors of a pair of systems x, y that both give us rho when the system y is traced out. What the unitary equivalence of purification says is that there must be a unitary operation u that acts only on the system y that transforms psi into phi. In other words, although these are arbitrary purifications of rho, and we don't assume anything about them except that they both purify rho and they're both states of the same compound system xy, they have to be equivalent in some sense, up to a unitary operation on y alone. We'll see a few examples that illustrate why this is interesting and what implications it has, but first let's see why it's true. Let's begin with a spectral decomposition of rho, which is the density matrix that both psi and phi purify. And just like we did when we discussed the Schmidt decomposition, we're going to assume that we've thrown away all of the terms corresponding to zero eigenvalues, so p0 through pr-1 are all positive real numbers, x0 through xr-1 are orthonormal eigenvectors of rho, and r happens to be the rank of rho. And by the way, just as an aside, notice how often we're reaching for the spectral theorem at this point. It's an incredibly handy tool, and in fact, we'd be lost without it. Anyway, now that we have a spectral decomposition row, we can compute Schmidt decompositions of our two vectors, just like before, and they're going to be almost exactly the same. The coefficients in the x vectors are the same because they come from the spectral decomposition of the reduced state, which is the same for both vectors. The only difference is that we may get different vectors for the second system. For the first vector, which is psi, we'll get one set of vectors y0 through yr-1, and for the second vector, which is phi, we'll get a possibly different collection, which we can call z0 through zr-1. So, we now have Schmidt decompositions for our two vectors, which look very similar, except that the vectors for the second system may be different. But these are Schmidt decompositions, so these two collections are both orthonormal. And so we can simply choose a unitary matrix U that sends YA to ZA for each A. You can always do that. Unitary operations are, in fact, equivalent to linear maps that transform one orthonormal basis into another. And if these two sets don't happen to span the entire space corresponding to Y, we can always extend them both to orthonormal bases using, coincidentally, the Gram-Schmidt orthogonalization procedure. And that is how the unitary equivalence of purifications is proved. In Lesson 4 of the series, we discussed the superdense coding protocol, which allows a sender to transmit 2 classical bits to a receiver by sending 1 qubit at the cost of 1 e-bit of shared entanglement. So I'm assuming that you're already familiar with that protocol, and the point of this example is to briefly explain how it connects to the unitary equivalence of purifications. Remember that the way that the protocol works is that Alice and Bob share an e-bit, or in other words, a phi plus Bell state. Alice chooses to transform that Bell state into any of the 4 Bell states, depending on the 2 bits that she wants to send, and then she sends her qubit to Bob, and he measures to see which Bell state he has. Notice that all 4 Bell states give us the same reduced state for Bob's qubit, which is the completely mixed state. And in fact, that's already enough to conclude that superdense coding is possible. All 4 Bell states purify the completely mixed state, so by the unitary equivalence of purifications, we know that it must be possible for Alice to transform the phi plus Bell state into any of the others by applying some unitary operation to her qubit. Of course, it's not difficult to come up with unitary operations that actually work, and they're very simple. But it's interesting nevertheless that we can reach the conclusion that this is possible without even thinking about the unitary operations themselves. And moreover, we can conclude that generalizations of superdense coding to larger systems are possible, provided that we have some way of generalizing the Bell states to larger systems so that they all give the completely mixed state as Bob's reduced state. And there are, in fact, different known ways to do that. The different setting to which the unitary equivalence of purifications has implications is quantum cryptography. And one of its most important implications is that it rules out the existence of an unconditionally secure quantum protocol for a cryptographic primitive known as bit commitment. So what is bit commitment? Bit commitment is an example of a cryptographic primitive, by which we mean a low-level task or procedure that provides some basic functionality, which can then be used as a building block to do more interesting things, like creating digital signature schemes or building zero-knowledge protocols, for instance. In the case of bit commitment, the basic functionality is that one player, Alice, is able to commit to a binary value of her choice to a second player, Bob, but her choice remains hidden until she chooses to reveal it. We require 2 specific properties from a protocol that implements bit commitment. It must be binding, which means that Alice can't change her mind once she's committed to a bit, and it must be concealing, which means that Bob can't determine Alice's bit until she chooses to reveal it. So it would be pretty nice to be able to implement this primitive using quantum information, because it's a useful primitive, but without any additional assumptions, it turns out to be impossible to do it perfectly with quantum information, or even close to perfectly, and the unitary equivalence of purifications reveals that. The idea, at a very high level, is that if there were a quantum protocol for bit commitment, then there would have to be a so-called purified version of that protocol, where we can imagine that Alice has a system A, Bob has a system B, And after the commitment is made, but before Alice reveals, the pair AB is in one of two pure states, psi0 or psi1, depending on the bit that Alice commits. If the protocol is perfectly concealing, then it must be that Bob can't tell the difference between the two commitments. So his reduced state must be the same for the two possibilities. However, that implies, by the unitary equivalence of purifications, that Alice can transform either one into the other by applying some unitary operation to A alone. So the protocol completely fails to be binding. There are details in there that I've swept under the rug, but the heart of the matter is that the unitary equivalence of purifications tells us that this primitive is not something that we can reliably implement using quantum information without additional assumptions of some kind. The last example of an implication of the unitary equivalence of purifications is a theorem known as the Houston-Joseph-Wooders theorem, or HJW theorem for short. Let's start with a statement of the theorem itself, and this is a slightly simplified version of it, just to avoid some technicalities so that we can focus on the main ideas. Suppose that x and y are systems, and phi is any quantum state vector representing a pure state of the pair xy. And now suppose that we think about the reduced state of the system x alone, and we come up with any way that we choose to express this reduced state as a convex combination of pure states, as is shown on the screen. So, for instance, the number capital N in this expression, which is the number of pure states we're averaging over, could be arbitrarily large, possibly much larger than the dimension of the space corresponding to x, or to y for that matter. And what the theorem tells us is that there must exist a measurement on the system y having n outcomes such that the following happens when the system y is measured. First, each measurement outcome appears with probability exactly equal to the corresponding probability in our expression of the reduced state of x as a convex combination of pure states. And second, conditioned on getting a particular measurement outcome, the state of x becomes the corresponding pure state from the convex combination. So why is that interesting? Well, it means that for any way that we choose to think about the reduced state of x as a convex combination of pure states, there's some measurement of y that effectively makes this way of thinking about the reduced state of x a reality. And what's remarkable is that this is possible even when the state phi is chosen first, and the convex combination is chosen later. As long as it's an expression of the reduced state of x, there will be a measurement of y that works exactly like this. So let's see how we can prove this. We start with two different expressions for the reduced state of x, which we'll give the name rho for convenience. Next, we introduce a new system z, whose classical states are the possible measurement outcomes, or equivalently, the indices in our convex combination. And now we can observe that the following two quantum state vectors, gamma 0 and gamma 1, which are both state vectors for the compound system xyz, are both purifications of rho. And just to be clear, when we're thinking about these vectors as being purifications of rho, we're thinking about the systems y and z together as a single compound system that gets traced out to leave rho. The first vector, gamma 0, is essentially the same thing as the original pure state phi, except that we're initializing the new system z to the 0 state. It's clear that if we trace out y and z, we'll be left with rho, so gamma 0 is a purification of rho. The second vector, gamma 1, is basically the vector we get by purifying rho based on the convex combination, just like I described earlier in the lesson. This time the system y is initialized, and I'm assuming just for simplicity that 0 is a classical state of y, but you could substitute any standard basis state, or in fact any pure state of y, into this expression, and it wouldn't make any difference. In any case, tracing out y and z again leaves us with rho. So the bottom line is that these are both purifications of rho, and therefore, by the unitary equivalence of purifications, there's a unitary operation u on the pair yz that transforms gamma 0 into gamma 1. And that's all we need to come up with a description of a measurement that does what the theorem says. A simple way to describe it is with a circuit diagram like is shown here on the screen. In words, we start out with the state phi, we introduce z initialized to the 0 state, perform u, and then measure the top system, which is z, with a standard basis measurement. Effectively what this does is to transform phi into gamma 1. And just by eyeballing the description of gamma 1, we can see that this does what the theorem says, which is that we get each outcome A with probability PA, and conditioned on getting A, the system X is left in the state psi A. And just to be clear, the measurement itself that the theorem implies the existence of is implemented by everything in the dotted rectangle in the figure. And if you want to know how the measurement can be described as a collection of matrices, here's an expression of them. I won't explain this part, and it's not really important for the sake of the example, but that is an expression of the measurement matrices in case you're interested. Next, we'll discuss fidelity, which is a measure of how similar two quantum states are, or alternatively, how much they overlap. We'll start with the definition, which might look a little bit mysterious at first glance, but we'll unravel it, and by the end of the discussion, I hope that I will have convinced you that it's actually a much nicer function than it might seem at first glance. And here's the definition. The fidelity between two density matrices, rho and sigma, is equal to the trace of the square root of rho times sigma times the square root of rho. We'll talk about it. First, let's just try to make sense of the definition itself. We have three square roots, and they all refer to the square root of a positive semi-definite matrix, which, as we discussed in the previous lesson, is the unique positive semi-definite matrix that squares to give us whatever matrix we're taking the square root of. Because rho is a density matrix, it must be positive semi-definite, so we can take the square root of it. And if we think about the square root of rho times sigma times the square root of rho for a moment, we see that it's also positive semi-definite, and in particular, we can write it as m dagger times m, for m being the square root of sigma times the square root of rho. And therefore, we can take the square root of it. In particular, we can compute a spectral decomposition of the square root of rho times sigma times the square root of rho. And then, to take the square root, we just need to take the square roots of the eigenvalues and leave the eigenvectors alone. And finally, we take the trace of this matrix. And because the trace equals the sum of the eigenvalues, we obtain the expression that we have right here. So that's probably something that you don't want to compute by hand in general, and this explanation might not offer very much insight into the fidelity or why we care about it, but hopefully it clarifies the technical meaning of the formula. By the way, just as an aside, sometimes people define the fidelity to be the square of the function that I've defined right here, and they refer to this function as the root fidelity. You'll see it defined both ways, which certainly has the potential to cause confusion, but it usually doesn't, because people are generally pretty careful about making clear which definition they're using, and you should be sure to do the same thing. To my eye, there really isn't a right or a wrong definition. I define it like this simply because I got used to doing it this way, and I do find that it's a little bit more convenient, I guess because I'd rather square something than take its square root later on when the need arises, but of course, you're free to make your own choice. But anyway, let me get back to the fidelity as it's defined here. There are other equivalent ways to define the fidelity, and it's actually a pretty remarkable function in that respect, and it can actually be characterized in some pretty interesting ways. Here's a pretty straightforward way to rewrite the definition in terms of the trace norm, which we saw toward the end of the previous lesson. I didn't go into too much detail about the trace norm, and in particular, I didn't even define it for non-Hermitian matrices, but it does have a simple enough definition. One way to define the trace norm of an arbitrary matrix M is that it's the trace of the square root of m times m dagger, or equivalently, the trace of the square root of m dagger times m. You get the same value either way you do it. And we can use that definition to simplify the definition of the fidelity as we have down here on the bottom of the screen. And that's nice because it reveals that it's symmetric in the two arguments. We can also express the trace norm of a square matrix M as the maximum of the absolute value of the trace of M times U, ranging over all unitary matrices U, which is not obvious, but it is true, and that gives us another expression for the fidelity. So here we have three equivalent definitions for the fidelity, and that's just the beginning. There are several other equivalent definitions, and we'll see a particularly important one, which comes from Uhlmann's theorem toward the end of the lesson. Okay, so that's fine, but what does it all mean at an intuitive level, and why should we care about this function? To answer these questions, it's helpful to consider the special case in which at least one of the two density matrices represents a pure state. If both states are pure, then the fidelity is simply the absolute value of the inner product between the two quantum state vectors, and in some ways this is a principal motivation for the fidelity itself. The absolute value of the inner product between two quantum state vectors is always a number between 0 and 1, and it gives us a natural way of measuring how much overlap there is between two quantum state vectors. And you can think about the fidelity as being a useful and well-behaved way to extend this way of measuring overlap from pure states to density matrices. If one of the states is pure and the other one isn't necessarily pure, then again we have a simple expression for the fidelity, which can be pretty handy, and that expression is shown right here. The fidelity has many interesting properties, and that's one of the reasons why people use it. It has a definition that isn't really all that nice, but it's a very useful function nevertheless, and it's often very easy to use, in part because of its many amazing properties. So let's take a look at some of them, starting with the observation that the fidelity between two density matrices is always a number between 0 and 1. It's 0 if and only if the states are orthogonal, meaning that the images are orthogonal subspaces, or equivalently that the product of the two matrices is 0. And the fidelity is 1 if and only if the two density matrices are equal. Every other case is somewhere in between, but intuitively speaking, the closer the fidelity is to 1, the more similar the states are, or alternatively, the more they overlap. The fidelity is also symmetric. I mentioned that a few moments ago. It's pretty clear from the expression that we saw for the fidelity in terms of the trace norm, but it's an important thing to recognize nevertheless. Next, the fidelity is multiplicative for product states, meaning that the fidelity between two product states is always equal to the product of the fidelities between the individual states. Here's a really useful property. If we have any two density matrices of the same size, along with any channel that takes these density matrices as input, the fidelity can only become larger when that channel is applied to both states. So in other words, in terms of the fidelity, channels can only make states more similar to one another. They can't make them less similar. And finally, for this list anyway, there's a pretty close relationship between the fidelity and the trace distance between states, which is defined as 1/2 of the trace norm of the difference between the two density matrices. The trace distance between two states connects strongly to how well we can tell them apart, which we discussed in the previous lesson in the context of state discrimination and the Hellstrom-Holovo theorem, while the fidelity quantifies how much two states overlap. So although they're not exactly the same thing, it's not shocking that there is a relationship between these two quantities. But in any case, these inequalities, which are typically called the Fuchs-van der Graaf inequalities, make this relationship mathematically precise. And it's pretty important that there's absolutely no dependence here on the size of the system we're talking about. We can see this relationship a bit more clearly with the help of a figure. If we have two states and we locate the trace distance between them on the x-axis and the fidelity on the y-axis, then the corresponding vertical and horizontal lines must intersect somewhere within this gray region. The most interesting region of the plot, by the way, at least practically speaking, is the upper left-hand corner of the gray region. In particular, when the trace distance is very small, the fidelity must be very close to 1 and vice versa. These inequalities get used very frequently, And part of the reason for that is that we often care more about the trace distance, ultimately, because it has a natural interpretation connecting with quantum state discrimination. But the fidelity has so many amazing properties that it's generally the easier one to work with. And as long as we're in the upper left-hand corner of the gray region, which is often where we find ourselves, we don't lose too much by converting back and forth between the fidelity and the trace distance. So those are some of the properties of the fidelity. There's lots more, but it's a good start, and hopefully the list is helpful for beginning to develop some intuition about the fidelity. Here's a nice example of how we can connect the fidelity to non-destructive measurements. It's a very handy fact known as the gentle measurement lemma. Suppose that we have a system X, a state of X represented by a density matrix rho, and a measurement on the system X described by a collection of positive semi-definite matrices. Let's suppose that one of the measurement outcomes is very likely to appear if we were to perform the measurement on the state rho. Just for simplicity, let's suppose that it's the outcome 0 that's very likely, and in particular, let's assume that this outcome appears with probability greater than 1 minus epsilon for some small value of epsilon that we don't actually need to specify. Epsilon is just some small positive real number. Now, we've described our measurement as if it were a destructive measurement, but we do know from the previous lesson that we could implement this measurement in a non-destructive way, and specifically, we could do it as we saw in our discussion of Neymark's theorem, and that works like this. Each outcome A appears with probability equal to the trace of PA times rho, and conditioned on getting that outcome, the state of X changes. In particular, in the case that we get the likely outcome 0, the state becomes the square root of P0 times rho times the square root of P0, all normalized so that we get a density matrix. And what the gentle measurement lemma tells us is that in this event, meaning that we do indeed get the likely measurement outcome, the state we obtain will not have changed very much from the original. And in particular, the fidelity squared will necessarily be larger than 1 minus epsilon. And this is great because this is completely general. We haven't said anything at all about the measurement or the state, except that one of the outcomes is very likely. So the lemma can be applied in many different settings where we'd like to verify something about a quantum state without disturbing it very much. So let's see how we can prove it. And for the most part, it's actually a pretty simple matter of calculating the fidelity between the pre- and post-measurement states. We can do this by using the original definition, and ordinarily that might leave us with a messy formula, but in this case we luck out because the thing inside of the outer square root is actually the square of a matrix that happens to be positive semi-definite, which makes computing the square root trivial. We can now use the cyclic property of the trace, along with the linearity of the trace, to simplify our expression as is shown on the screen. Notice, by the way, that these are all equalities, so we haven't approximated anything at this point. We're really just simplifying. But now we do need an inequality because we'd like to get rid of that square root in the numerator, and we can indeed do that if we're willing to settle for a lower bound. And if you're interested in the details for this part, you can get the inequality pretty easily by considering a spectral decomposition of P0. The eigenvalues of P0 have to be between 0 and 1. That's always true for matrices that describe measurements. And once we know that, the inequality follows pretty directly from the fact that taking the square root of a number between 0 and 1 can only make it larger. Another way to say that is that squaring a number between 0 and 1 can only make it smaller. We can now simplify just a little bit more, and we get the square root of the trace of P0 times rho. Finally, squaring both sides and plugging in our bound on the probability gives us what we want. So, the formula for the fidelity isn't the nicest or easiest to use formula in the world, but here it actually works pretty nicely. To conclude the lesson, we'll take a look at Uhlmann's theorem, which is a fundamental fact about the fidelity that connects it with the notion of a purification. What the theorem says in simple terms is that the fidelity between any two quantum states is equal to the maximum inner product in absolute value between two purifications of those states. In a bit more detail, suppose that rho and sigma are density matrices for some system X, And suppose that Y is a system that has at least as many classical states as X, and therefore we're guaranteed that both of these states have purifications that are quantum state vectors of xy. We can then express the implication of the theorem in the form of the equation shown on the screen. The fidelity between rho and sigma is equal to the maximum absolute value of the inner product between phi and psi, ranging over all phi and psi that purify rho and sigma respectively. So let's clean this up and work with the precise mathematical statement going forward. What we'll do now is to prove the theorem, but first it's worth taking a moment to appreciate that it offers us a pretty intuitive way of thinking about the fidelity. It also happens to be quite useful in its own right, for instance, to prove even more interesting things about the fidelity. To prove it, we'll start with spectral decompositions of our density matrices. No surprises there. Once we have spectral decompositions, it's easy to come up with two specific purifications of these states. But here we're actually going to play a trick. Notice that in both cases, we don't have a standard basis vector as the second tensor factor like we did earlier in the lesson, but rather we have the same vector as in the first tensor factor, except that it has a bar over it. And that means the entry-wise complex conjugate of these vectors. So in other words, we're basically just taking a second copy of the eigenvectors, but we take the complex conjugate of each entry, and we'll see why we do that in a few moments. But it's not at all obvious that we should do this, and that's why we call it a trick. In any case, these are purifications of rho and sigma respectively, and that's true by virtue of the fact that our eigenvectors are orthonormal, and therefore so are their entry-wise complex conjugates. And now we can apply the unitary equivalence of purifications, which says that every purification of our two states can be obtained by applying a unitary operation to the system that gets traced out for the specific choices of purifications that we just made. The unitary operations don't have to be the same for the two purifications, of course, so here we're using the letter U for the first one and the letter V for the second one. So the point is that every purification of our two states can be written as we have on the screen for some choice of unitary operations U and V. And now we can take the expression from the theorem and simplify. If we plug in our expressions for phi and psi and simplify a little bit, we get the expression that's shown here on the screen. Now, there are a couple of steps in there, and I haven't shown the details, so you know what to do if you want to do it. But let me mention that the reason why we chose the purifications as we did was to allow this inner product to simplify in exactly this way. And in particular, we put the complex conjugates in there so we'd effectively be able to flip around the inner products in the second tensor factor to get the specific form that we have right here. We're almost there. Now we can use the cyclic property of the trace along with the spectral decompositions we started with to get this expression. And at this point, we can employ one of the alternative ways of expressing the fidelity using the trace norm, and we're done. Certainly, there are details in there that I glossed over very quickly, and it's the kind of proof that you really do need to work through yourself to fully grasp. But hopefully this gives you the basic idea. And as usual, you can find more details in the written content for the lesson, which is linked in the video description. And that's the end of the lesson, which has been about purifications, fidelity, and the connections between them. And it's also the end of the unit, which has been about the general formulation of quantum information. I hope you will join me for the fourth and final unit of the series, which is on quantum error correction. Thanks for watching.